Welcome back. This is part 5 of the series. In this video, we'll cover 2 examples that show how to generate sample points using VASA. You'll also learn how to create density maps and use proximity operations. So let's begin. Here we are in Dynamo. We'll file open, and we'll be looking at examples 11 and 12 today. If you don't see examples 11 and 12, it probably means you have an old version of VASA installed. So make sure you've got the latest version of VASA and go ahead and open example 11, path density. Now, this example shows us how to create a density map of various paths through a building. And it takes a bit longer to run than some of the other graphs we've seen so far. So I'm actually going to show you really quickly how to speed up in case you find that necessary. So remember this the finest level of detail parameter, and if we decrease that to 3, it'll coarsen the voxels and make the calculations go faster. If you change the finest LOD to 3, I'd recommend reducing the agent diameter offset, maybe from 7 to 3. And then also find this min diameter offset, which I'll explain later, but change that from 15 to say 7. And if you make those changes, the example will run faster. But in this case, it's run, so we'll just go ahead and take a look at it with the high resolution. Okay, so here we have a bunch of paths that have been calculated through the building. All these paths come from this point that's just outside the main entrance, and you can see there's some coloring. So the red, the color indicates the extent to which the paths overlap. So these denser areas where the paths overlap, right by the source point here, you have this red color. Then as the paths diverge, it goes to orange, yellow, green, and finally blue, where you've got these just individual paths. So that's the density map, and let's see how to create it. So we'll go. Let's go here to where the paths are being displayed and just hide that. And we'll go up here to where the building is being displayed, and we'll just disconnect the color, the translucent color, so that we can see the building a bit more clearly. And I'll just change the orientation here. Okay, looking back at the graph, the example starts off the way what most examples do, where we load up the triangles from STL files. We voxelize them. We use the union operation to create one voxel model, and then we create a path model to enable pathfinding. And then in this case, we've created a distance field, which computes all the distances from a point. And we've chosen this point right there, just outside the main entrance. And that's all been done before, but now is where things get a little different from the other examples. So after we create the distance field, we now generate sample points using this distance field .generate sample points node. So let's take a look at what that does. Before we go any further though, so I don't forget, I'm going to take this node here and freeze it so that as I change the sample points, it doesn't go and recompute everything. Okay, let me preview the sample points. And now you can see sample points that have been automatically generated throughout the building. And I'm going to just going to move this group over here so it's out of the way. And the display has gone a bit strange because I've selected a point node. I find that if I just select it again and deselect it, usually clears up. And now let's take a look at the sample point parameters. So these parameters control how the sample points get generated. And the most important parameter here is the spacing. So right now it's set to 5,000, which in this case is 5 meters. So it's trying to generate points that are approximately 5 meters apart. It's very approximate. And that's the approximate spacing. And if we slide that down to 4 meters, we'll see the number of points increase. And then let's just keep on reducing that. 3 meters. That's 3 meters. Go to 2. And let's go all the way to 1 meter. And take a closer look. That's still 2 meters. Now it's 1 meter. So so you can see, it's placed points everywhere here, but in some parts it almost looks like a grid, but not quite a grid. What it's trying to do is it tries to conform with the walls or with the geometry. So if we did have a big wall that sort of cut through the building diagonally, the points near the wall would tend to align with the wall. But they're not restricted, of course, to a grid. They have a slightly random look to them, and that's intentional. The idea is that by changing these parameters, it can generate a whole bunch of different patterns of points, and a small change in the parameter should lead to a small change in the points generated. So if I change this to 4.9 meters, I'll get a distribution of points. And if I just change that slightly to 5, then the distribution will change slightly. And the idea there is to be able to use this for general design. So you could imagine having a general design process choose that spacing parameter, so it could potentially hone in on a certain distribution of points that might lead to better design. But right now we're just using it to pick some points for analysis, and so that's the spacing parameter. Another one is this min diameter offset. That just restricts the locations where it can actually place points. So what we want to do, so if we were to set that to 0, or no, let's set that to 1 rather, we'll find that it starts placing points in places that we didn't really want it to place points. Like it places points on each step here, for example. We could go to the other extreme and set it all the way to a really high number like 45, and then it will tend to eliminate points from smaller areas like the small passageways and the landings of the stairs. Let's just undo those changes and go back to what we had initially, 15, which will end up placing a point on the landing there and a few points around. So that's something that can be changed. And finally, there's this min distance parameter. There's also a maximum distance that we're not using. It just defaults to -1, which actually means infinity. There's no maximum, but the minimum is set to 18 meters. And that's just saying that the points have to be at least 18 meters from the source point. So if we just set that to 0, we'll see that it's going to place some points on the outside of the building. Some models may not have a ground outside the building, so in that case you wouldn't maybe have to worry about this, but in this case it's placed points outside, which we didn't want. It's also we can also see a point just inside the main entrance there, and if we set this to what it was before, just undo the change, 18 meters, it'll get rid of those points outside. It'll also end up incidentally getting rid of the point that's just inside the building, because it is within 18 meters of this source point. So yeah, so that's how you generate sample points. Okay, so what comes next? I think let's unfreeze this node. And see what's happening. So once you generate sample points, you can basically do whatever you want with them. There's a whole there's different things you could do. In this case, we're going to generate paths from every sample point to the source point. And to do that, we're going to reuse that distance field. So we take that distance field there that we used to generate the points, and we use that same distance field to calculate paths, from each of those sample points to the source point. So the source point's already part of the distance field, so we're just passing in that list of 118 sample points, and that's giving us 118 paths. And now once we get those 118 paths, we create 118 voxelized paths. Let's actually take a look at what that looks like. So let's right click and bring up a display voxels node. Let's choose color, say purple. And here are all the voxelized paths through the building. Again, I just want to stress that you don't have to use the same distance field that you use to create the points in order to use the points. It's up to you. But in this case, that's what we're doing. So we have these voxelized paths. Now we're going to expand them and make them thicker so that they overlap a bit more. So let's just take a look at the result of that operation. So now they've been expanded horizontally with this surface operation. No, before we expanded them, we used this enlarge node to enlarge the extents because all of the path models had extents that were fitted to the path, and if you just enlarge the surface, it'll go out beyond the extents and get cut off. So we enlarge the voxel model slightly and then expand them. Just a little detail. Then once we have these expanded paths, we're going to make sure that they don't go. We're going to make sure that they haven't been expanded too far, like off the edge of the traversable areas. So if we go into the building, for example, you can see that when it's expanded them, it's actually sort of expanded them right off the edge of these stairs, for example. If we're not careful, it could actually expand them right through a stair. Sorry, I'm having trouble navigating here. But you can see from behind the staircase, you can see that the expanded path voxels are going off the edge of the staircase. So they're a little bit too wide. So what we're doing here is we're going to intersect it with the reachable area, reachable voxels. So these are the voxels that are reachable from the source point. And we're going to take that and intersect it with what you just saw, the expanded path voxels. And when we intersect the two, we'll still be looking at the path voxels, but they won't go like off the edge of the staircase and other strange places. So yeah, and you'll notice that in order to use the intersect on a whole bunch of paths at once, we had to be a little bit clever and use these fancy list operations in order to put the lists in order to sort of pair up the voxel models in a way that would let us do the intersect all at once. So there's some list operations there, but in the end we end up with a set 118 voxelized paths that have all been expanded, but not too far. Okay, so that's what we have so far, and now we want to create that density map that had all those different colors. So if I just hide this and display the final result, you'll remember that we had all these. Actually, let me just actually connect this and make the walls translucent again. So you see that it almost looks like there's one voxel model, and that's being colored different colors. that's not what's happening. What's actually happening is there are 10 voxel models coming out of this density map operation. And then here we're getting 10 colors from this. This is just a standard color range. It comes with Dynamo. You can change the color range and use a different set of colors, but we have 10 voxel models, 10 different colors, and that's what's being displayed. So it's so what the voxel that you see in red, that's one voxel model, or orange is another voxel model, etc. So how are we getting those voxel models? So we take that 118 voxel models for each path, and we use this density map to kind of reorganize them and give us a different voxel model for each density level. So let's see what's happening there. So first we go into this code block, and we bring the voxel models for each path right through the code block, and that goes straight into this density map operation. Just to show you what that operation is, it's under VASA operations. There are these special operations, and there's density map. There's also a density map with weights in case you want some of the input voxel models to say count as 2 or to count as 0.1. You can give them all weightings, but here we're just using a standard density map. So we give it the input voxel models, and then we give it a set of levels. So the rest of this code block, all it does is calculate these levels on line 5. There's this extra line, line 6 there, that's not being used. That's a mistake. That shouldn't be there. You can go ahead and delete that if you want. The code block is calculating these levels, and the levels that are being used right now are 1, 4, 9, 16. They're all perfect squares, right? 5 squared, 6 squared, etc. So what that's saying is that for the first density level, the one in blue, that's showing you all the regions that have at least one path going through it. But then the next one, which is probably a greenish color, it has level 4. That means there has to be at least four voxel models that have a filled voxel at that location, and it's set or 9, then 16. For the red voxels, there has to be at least 100 sets of these voxelized paths that all intersect there. So it gives you the density levels. And we don't have to use perfect squares. Like, in fact, actually, if we use this line 4, this sequence here in line 4, and assign that as the level, we'll see that that one just goes up linearly. So when that it's calculating, but when that updates, we'll see a change to, there it is. We'll see now that the levels just go up linearly, 1, 2, 3, 4, 5, all the way up to 10, and that's changed the colors. But it's actually, it's possibly a little more interesting now, because now we can see, okay, now we see a lot more red throughout the building, and we can see, for example, that that these 2 staircases right on the ground floor are both red, so they're well used, or this is assuming, of course, that people actually take the shortest paths. They may take a longer path if in order to use a nicer route through the building, for example. But in this case, it's predicting that these 2 staircases near the bottom would be well used. But as you go from the 2nd floor to the 3rd floor, only this one on the right is being used frequently. This other one is not being used, because actually it's shorter. If you want to get to this wing, this long wing here, it's actually showing you that it's shorter to take the stairwell here to the 3rd floor and then go across, rather than taking this staircase right here. People may just still decide to take the staircase out in the front because it's more open, but it's interesting that the shortest is actually shorter to take the stairwell to get to the 3rd floor. So that's something that we can see there. Of course, when we have this linear scale, we only go up to 10. So once we get more than 10 voxels intersecting, it just shows up as red. So that was one of the advantages of having the editor color scale that went all the way up to 100. But anyway, the levels you can choose whatever you want. If you want, you could just choose one level. So if we wanted, we could just have a list with just 10 in it and connect that up, and that will just, instead of giving us 10 voxel models coming out, it'll just give us one, and it'll be a voxel model showing us all the areas where at least 10 voxels are filled from these 10 different voxel models, or 10 of the 118 voxel models will be filled there. So then we're seeing these densest areas in terms of where the shortest paths overlap. Okay, so one more thing I want to show with this example. So let me actually we delete that and go back to what we had before with the original set of levels. And while it's calculating, I think I'll create a let's create a get item at index node, and we'll create an integer slider. And there were 10 density levels, so we'll have this go from 0 to 9. That would give us all 10. I'll start at 0. And let's plug in that list and just choose one model. Let's turn off that display, and I'm going to move this display over here so that we're just going to display one of the density levels at a time, and we'll show that. Okay, so this is the density level where only one voxel is present. So it gives us the ends of the paths, and as we increase the slider, we go to the next density level where the paths start to overlap with each other, and the next level, and then as we go up, we just see the areas where all the paths start to converge near the bottom, and as we go up, we get closer and closer to the source point. And the last level gives us right where all the paths basically intersect. And now let's reduce that and take this model at level 5, and let's just take a closer look at that. So let's see. So we just see like there's these two areas here where we see some filled voxels, and let's see what the extents of this model are. Let's see what the extents are. So let's go to well, I can just type in extents. Then I have to make sure I'm getting the one that takes a voxel model as input. So let's take a look at that, and then display extents. And okay, it's showing us that the extents of this voxel model coming out of the density map is the extents of the entire model. So it didn't shrink the extents at all. But now there's some operations that we want to take a look at. So let's go into special operations. We're already there. Let's look at the auto crop first. So the auto crop operation will crop the model so it's just big enough to contain all the filled voxels. So let's go insert that in the middle there, and now we can see it crops the model just so it fits the voxels in purple there. So that's the auto crop node. Now let's take a look at the auto split node. What this does is it creates a separate voxel model for each connected set of filled voxels. So that's going to take a second or two to run, and now we can see it's actually given us 20 voxel models from the one, and it's given us a separate voxel model for each separate sort of chunk of filled voxels. So if we it's separated it separates it so that if you were to use a fill operation, a fill from point operation, you'd have to, it would take you 20 different fill from point operations to fill up all these all these areas. So one thing, so we notice that there, it's giving us separate voxel models every time they're connected just at a corner. Suppose that we wanted to have this be connected in just 2 groups, say. Well, then we need to make sure that these corners got connected up. So we want to fill in some voxels right at the corners of 2 filled voxels. So there's an operation that does that if we go into surface operations, and I don't believe we've seen this in the previous videos, but I'll create this expand one voxel node, and if we insert that right here, and before we do that, I'll just set these parameters. So if we set the horizontal adjacency to 2, that means everywhere you've got at least 2 voxels adjacent to the voxel that are filled, it's going to fill in an empty voxel. So let's see what that looks like. So everywhere that we had an empty voxel with 2 filled voxels beside it, that will become a filled voxel. So it's going to fill those up, and actually I'll just display the result of that. And so that's going to cause these areas to become just one connected area. And then let's create one more. Let's create one more expand by one voxel node, and this time we'll set the horizontal adjacency and vertical adjacency to 1, and that will get us all. That will fill in all of these corners in the vertical direction. So all the steps, for example, where you have a corner here, it's going to fill in one voxel where there's a horizontally filled voxel next to it and a vertically filled voxel. So let's insert that into the sequence. Okay, and so now the steps became all connected. Okay, so now after we split it, we performed the auto split operation. We've ended up with 3 voxel models. These 2 over here are still disconnected, but we have fewer than before. Okay, that's just to show you some of these operations. All right, I think we're done with this example. Let's move on to the next one. So, example 12, sensor coverage. Okay, this one is also uses this sample point generation feature, but it uses it for a different purpose. So it's placing sensors using that sample generation. You say it's placed sensors all around. Some of these sensors are oriented downwards. These colors represent sort of the field of view of these sensors, and some of them are pointed down, some of them are pointed sideways. And there's no particular kind of sensor. I mean, the vertical ones could potentially, they could potentially be passive infrared sensors, perhaps to activate an automatic lighting system. The horizontal ones look a bit more like security camera. Looks like security camera coverage, but it doesn't really matter what it is. It's just demonstrate the features of VASA. I mean, the yellow ones could even be lighting fixtures showing an area that gets lit from overhead lights. But you can use this for a variety of purposes. Let's just take a look at the graph, and there's there's this wall offset parameter, and when we change it, it'll actually change the distribution of sensors. So if we increase that, it'll give us more of the horizontally oriented sensors, the ones in blue. If we increase it all the way, I think we'll get only the blue sensors. And if we decrease it, we'll get more of the downward oriented sensors with the yellow colored areas of coverage. And if we go all the way, we'll get, they'll all be yellow. So let's set that to what we had initially. And let's actually go and turn off the sensors. And we'll just go through step by step how we created this. So the oops, get back on. Huh, that's funny. Must have clicked too many things at once. Anyway, it's working now. So again, we're just going back to the beginning. We create the voxel models. We create a path model. We're not actually calculating paths, but you need to create a path model in order to get the sample points. So we do create a path model, and then in this case, we're generating sample points directly from the path model. So if we go on the left and go into pathfinding, we can there's a distance field. We see that in distance field, we have a generate sample points node. We also have a generate sample points node in path model. So there's two different ways to generate sample points. If we generate the sample points from the path model, it'll tend to give us more points. For example, it'll tend to put points on the roof of the building. Let's just see why it's doing that. So if we go to look at the path model, if we look at the traversable voxels, and if we display that, we'll see that the traversable voxels includes the ceiling. It includes like this rooftop here. It includes areas that you couldn't actually get to, from say a point on the ground. So that's the difference there. So we do get a lot more points. We get some points that we don't want because they're outside the building. So what we do in this example is after we generate the points, we eliminate some of them. So we're actually going to eliminate the ones that we think are outside. And the way we're doing that is we're actually we're just doing a simple analysis where we're doing here it is. We're doing a visibility from direction. So we're looking at all the voxels that are visible from above. And then we're going to remove all of the points that are in that area, because we're saying if it's visible from the sky from above, we're just assuming that it's outside. That's not true for all buildings, but it does seem to work for this example. So we do that visibility calculation, and then what we do is we take the sample points, and then we use this voxel iterator node. So there are voxel iterators and iterators, voxel iterator by voxel model and point. We give it the voxel model you see here in purple, and then it gives us a set of iterators, one for each of the sample points, and then we ask whether the voxel at that location is filled, either true or false. So in some of these are false. That means that the point is in this empty area. If it's true, it means it's in the purple area there. Then we apply a mask. So we filter the list. And in this case, we're getting rid of all the points in which is filled is true. So we're getting rid of all the points that are in the purple areas, which we consider to be outside. And then we take the output of that, and the points that that are in that the acceptable area, we translate them up by 1 meter, and this gives us our final set of points. I'm going to display those translated points. I'm going to turn off this display. And so these are the points that we consider to be inside the building. So there's a bit of a few steps to get that list filtered. So yeah, so we got our set of points, and now what we're going to do is we're going to take some of them and convert them into wall-mounted sensors. So what we do, this is where we use these proximity operations. So under VASA operations, proximity operations, you've got you got four nodes to choose from. Here we're using nearest filled horizontally. So it's going to take each of these points, each of the points you see there, and it's going to find the nearest filled voxel, and then it's going to give us a voxel iterator for the point that's in the nearest filled area. So I mean, this would actually give us a point that's right inside a wall, but we don't want that. We don't want the points to be right inside the wall. We want them to be just on the outside. So what we do here is we take the walls and we expand them by 1 voxel in the X direction and 1 in the Y direction, which makes the walls thicker, so that when we find the nearest voxel, it'll actually be at a location that's just outside of a wall or just outside of a column. So we have our list of iterators. Now there's a maximum distance. That was that parameter I was changing earlier, this wall offset. So it only searches within a 27 voxel diameter area. So if you have a point that's in the middle of a room, it's not going to find a wall in that area. But if you have a point that's near a wall, then it will. So we're going to end up with some of these voxels being valid. But here we're using the is valid node. Some of them are valid, means it found a point near a wall, and some of them are invalid, they're false there, and so it didn't find that point. Now here we're filtering the list. So in this case up here, we're taking the points that were near a wall and finding the we're taking the iterators, I should say, that were valid, that were near a wall, and then getting the center points. And so if we preview that, and maybe I'll hide this preview, these are the points that are near a wall or near a column that are going to get turned into wall-mounted sensors. And so how the wall-mounted sensors work is we use a visibility within pyramid operation, and we give it a vox model representing the walls. We give it those points that are near walls. We also give it a direction, and the direction we give it is the direction from these points to the original locations of the points. So if we so remember we had the points that were originally generated, and then they got moved. So actually, let me just turn this on here. Actually, so we had points like this one that were generated originally, and then we found the nearest point on the wall Now we're using a vector from the wall point to the original point, and that's the direction that the sensor is going to face. So we do that visibly within pyramid, and when we show that, it'll show that this is the way that the sensor will, it shows us the direction the sensor will be facing. It shows us the area that will be covered by it. Okay, so that accounts for the wall-mounted sensors. And now, there's quite a few steps in this example, but now we take all the points that we haven't used so far. So let me turn off these previews. We take all the points that did not result in a wall-mounted sensor because they were too far away from the walls. And we now use a different proximity operation, nearest filled along Z, and we give this operation a lower offset of 0. That means it won't look downwards, but it will look upwards. So it will look in this case up to 12 voxels above for a filled voxel. And like before, we don't want to use the walls and ceilings. We want to expand it slightly, because if we pass in the original geometry, we get points inside the ceiling. We want a point just below the ceiling. So we actually take the original building voxels and we expand it downwards first, and we expand it downwards by the default value of 1. And then, so now when it finds a nearest filled voxel in the above, it'll find the voxel that's 1 below the ceiling. Okay, so then we go through the same process as before. We'll get a bunch of iterators. In this case, I believe they're all true, or well, most of them are. And then it will we'll filter the list. Then we'll find those voxel locations that are just under the ceiling. So you can see that we've got sets of 2 voxels, one right above the other. And then we take those ceiling points. We do, in this case, a visibility from cone operation. From that point, pointing down using a vector between the ceiling point and the original point. And then that gives us our downward oriented cone. And when we display that, this is what we end up with. Let me just turn off the points there. Okay. And there were some points on the landings and a few locations that didn't actually get used. But this is this is how that's done. Okay, so we'll leave it there. There's a variety of things that you can do with by generating sample points. We've seen the creating paths and creating a density map from the paths. We could also create sensors or other elements. So hopefully this inspires you to be creative and see what other applications you can do with these features. All right, thanks for watching.